Shneur Gambarova, and I am presenting my assignment for week 5, topic 5. So I'll go ahead and share my screen. Share. So here I divide it into 2 parts since it is a big assignment and there are 2 main parts, 2 different data sources, so I divided them by 2. So let's start with the task 1. So task 1 is to conduct a hypothesis test to determine whether there is a significant difference in the mean weight between males and females. So I used the dataset from the Kaggle, and this dataset's name is 500 persons, gender, height, and weight. And here I am, as usual, importing my libraries and then just looking at the data set itself. I wanted to make sure that there are no nulls, so it is easier to analyze. And then I visualized box plot to look at the distribution of the weights, and you can see here visually that the distribution is very similar by gender. For male and for female, they are pretty much same. And the second way, I try to perform 2 sample t-test and try to calculate the difference between means. And as you can see here, p-value is 0.8, which means there is no significant difference in the mean weight between males and females. Second task is we are using the same data set and we are calculating the correlation coefficient between height and weight. So how are they correlated? Does the change in one of the variables mean that it will affect the other variable? So here I calculated it by using a correlation function, and as you can see, the correlation is 0.0004. And as we know, correlation can vary between -1 and +1. If it is closer to 1, it means there is a really big, like high correlation. And if it is close to 0, that there is no correlation. The change in one variable doesn't affect to any change in the other variable. And negative means negative relationship, which means opposite relationship, and positive means positive relationship. And another way to look at the correlation, it's of course to look on visual scatter plot. So I try to visualize it here, and as you can see, there is no correlation. If we draw a line, none of the data points are close to the line, and there is no clustering, nothing. So it is all random, so we can say that there is no correlation between height and weight, which means you can be high or tall or short, it won't affect your weight. Task 3. Build a linear regression model to predict weight based on the height. So first, I'm trying to build a model and see does it fit. So as you can see here, we have our summary. So, and here standard errors assume that the covariance matrix of the errors is correctly specified. And we are trying to check for the assumptions of linear regression. We are checking, is there multicollinearity or heteroscedasticity, where, for example, here we can see that p-value. So since both of the p-values are greater than 0.05, we fail to reject the null hypothesis of homoscedasticity. This means there is no evidence of heteroscedasticity in the regression model. Yes, since there is no relation between height and weight, we can't predict the height based on the weight. So task 4, build a multiple regression model to predict weight based on height and age. So here we are going to multiple regression model. So if in previous model we had only one independent factor, here we are adding another independent factor. Excuse me, where's task 4? Yeah. So here we are adding gender. And since gender was male and female, a string type, I had to convert it to the integer so I can work with it. And so here you can see our summary. And here we are checking for multicollinearity, and as you can see, the calculations, VIF values for both height and gender are approximately 1. This indicates that there is no significant correlation between these variables and other predictor variables in the model. And the VIF values for const is very high, which indicates there are a high degree of multicollinearity between this variable and other predictor variables in the model. This could be due to the inclusion of an intercept term in the model. And the last assumption here is heteroscedasticity. So here again, both p-values are greater than 0.05, and we fail to reject the null hypothesis. And this means there is no evidence of heteroscedasticity in this regression model. Yes, and another. So part 2 is I have task 5. It is, we are using a data set and build a linear regression model that violates one of the assumptions. So here I'm using the medical cost personal data set from Kaggle and doing the same summary. So this model has high R-squared value. 0.6, which means that 62% of the variation in the charges can be explained by the smoker variable. However, this model violates the linearity and normality assumption of linear regression. We can check this by plotting the dependent variable against the independent variable and see is there any correlation. So we are using scatterplot, and as you can see, so this plot shows that there is no linear relationship between these charges and the smoker variable. Instead, there are two distinct groups of charges based on whether the individual is a smoker or not. The linear regression model is not able to capture the difference and instead fits a straight line that splits into the two groups. And last, this is the last 6 task. How can we compare the performance of linear and nonlinear models? So we can look at these measures. R measures how well the linear regression model explains the variance in the independent variable. So higher values closer to 1 indicates a better fit. MSE, RMSE, and MAE. This matrix measures the difference between the predicted and actual values. Lower values indicate better performance. So we can evaluate the nonlinear model's performance using similar metrics. Compare the R-squared and error metrics of the nonlinear model with those obtained with the linear regression model. A higher R-squared and lower error metrics in nonlinear model might indicate better performance. We should ensure nonlinear model we are comparing is appropriate for our data and provides a better fit compared to the linear regression model. The choice of the appropriate model depends on the complexity of relationships in our data and accuracy of the predictions we require. So, thank you so much. Bye.